Welcome back to ECE 442-542. In this discrete equivalent session, we are going to be looking at doing the numerical integration strategy in a state space representation. So here in this piece, let me go ahead and summarize what we have already derived based on numerical integration for the forward, the backward, and the bilinear or trapezoidal strategy in a table. And then we'll use those substitutions, the z expression substituting in for the s expression, in a state space representation structure, and see if we can then find the appropriate state space representation matrices for the discrete time discrete equivalents in a state space form. Remember, in this particular numerical integration strategy, we're looking at scenario number 1, where we're really just trying to capture the input-output behavior of a specific transfer function. Here I'm calling it h of s. That could be a filter. We're not preceding this filter with a zero-order hold. We don't have any other dynamics that we want to incorporate into this discrete equivalent in going from the continuous time setting or converting capital H of s to capital H of z. We just want to make that immediate substitution or more direct substitution, and this is what we were calling scenario number 1. We derived these numerical integration strategies for different ways of, remember what we were doing. We were actually trying to determine a way to find the area under a curve. And we did that by really just adding on to what we already have an additional sliver of area. And that sliver of area that we were adding on to now really just was determined by either the trapezoidal connection or going forward with our area, or we were going backward from the present time and getting this area that way. So we had the forward, the backward, and the trapezoidal strategy for adding an additional sliver of area to the existing area that we'd already determined. And that then allowed us to find a z expression that we could use to substitute in for the s variable wherever that appeared in our original h of s transfer function. In the forward case, we would replace s with the factor z minus 1 divided by capital T, where capital T is our sample period. In the backward strategy, that changed a little bit. It was now in the numerator this factor z minus 1, and in the denominator it was still capital T, but that capital T was joined by an additional z. Meaning, if somebody said, oh, I want you to obtain a discrete equivalent for using a numerical integration strategy using the backward attempt or the backward technique, then everywhere you would see an s, you would replace that s in capital H of s with this expression, quantity z minus 1 over tz. The trapezoidal or bilinear meaning it's a quotient of two linear expressions, and this is really sort of the average of the forward and the backward. It's now finding maybe a better approximation to that sliver of area. It's now 2 over capital T times this ratio of factors of z, in the numerator z minus 1 and in the denominator z plus 1. Those were our substitution relationships that we would use in place of s. Wherever s occurred in the h of s expression, we would replace it with one of these expressions in Z, whether we wanted to do the forward, backward, or trapezoidal, or Tuscan, depending on what you're reading. The trapezoidal might be referred to as bilinear, it might be referred to as trapezoidal, it may be referred to as Tuscan. But any of these then is what you would use to find a numerical integration discrete equivalent. What we want to do now is use these three one at a time. Obviously, we're not going to use them at the same time, but we will now apply the forward strategy for a state space representation. Then we'll find the backward strategy, and then I'll leave it up to you to use the trapezoidal, but once you've seen the forward and the backward, maybe it will be a little bit more doable to find the bilinear representation in the state space setting for the discrete equivalent. Let's set that up. Here's our discrete equivalent for a state space representation, and we want to use a numerical integration strategy. Here I'm assuming that we have this model in the continuous time setting. We have a system matrix, capital A, we have an input matrix B, and here note that the input I'm actually using as E, and the output is U, so that if you were looking at this in terms of a system, here is our input E, and here is our output U, where this might actually be more, and this is why I don't call it a C or a D, because you're going to get it confused with this C or D matrix. So let's just continue to call it an H of S, but this now might have been a filter or a controller that's in front of a plant that we're trying to control. But the input to that is now E, the output is U. The state vector is X. We want to now convert that into a state space representation, where now the system matrix in the state space representation is capital Phi, the input matrix is gamma, the output matrix is H, and the direct feed-through matrix is J. And you might note that the state vector in the discrete time setting is not necessarily little x of n. It can be something else. So here, this is now our state vector, and it's not necessarily the discrete time or the discretization of the state vector x in the continuous time setting. It may actually be something else. So just keep that in mind as we're going through this. Sometimes it may actually be x of n, but in general it's a new vector, but you can relate that new vector to an x of n vector, and hopefully that will become clear as we work through this process. Here's what we have then. For the analog setting, we have a system, which again could be a controller or a filter. The input is E, the output is U. We now want to find these different matrices in the discrete time representation, Phi, gamma, H, and J. And, for example, Phi, the system matrix in the discrete time representation, may involve a combination of the A matrix, B matrix, C matrix, D matrix, and the sample period T in order to produce capital Phi. What we're trying to find now are those functions that will yield Phi, gamma, H, J. If somebody gives you A, B, C, and D, and they tell you what the sample period is, T, or you have to find it, and you can find it by looking at the eigenvalues of A, or if you're going to modify, but in this case it's usually now the eigenvalues of A, you would maybe sample at 30 times the fastest eigenvalue of A, and that would be your capital T. You now have A, B, C, D, and T. We want to know, how do you use those matrices to come up with phi, gamma, h, and j, so that we can now have a state space representation between the input E of n and the output U of n. Here's the process. Step 1. The very first step is we want to Laplace transform the continuous time state space equations, and since we're really looking for a transfer function representation eventually, we're not going to worry about the initial conditions. Now, what happens when we Laplace transform this state space representation? Remember, what happens when we Laplace transform a derivative? That's now in the frequency domain. That's just a multiplication by s. And now we're in the transform domain. We now capitalize little x of t, and we're now saying, oh, we now have the Laplace transform of little x of t, which is capital X of s. That's now equal to the Laplace transform of the right-hand side. There's no derivative action on the right-hand side. We simply have a constant matrix A, and we can Laplace transform little x of t to obtain capital X of s. B is a constant. That can factor out of the Laplace operation, and we now Laplace transform little e of t, which becomes capital E of s. The right-hand side then becomes A capital X of s plus B E of s. Our input, remember, is E. That's the dynamic equation Laplace transformed in our continuous time state space representation. What happens when we Laplace transform the output equation? Everything is at the present time. This is now a non-dynamic relationship between the output U, the state vector x, and the input vector E, and we can now use that. That's just a linear equation. We can Laplace transform both sides, and we have capital U of s is equal to C capital X of s plus D E of s. What we now want to do is replace the operator. S is an operator. X of s, U of s, E of s, those really are just functions of s. It's not the operation s in the argument of x, e, or u. What we now want to do is actually replace this operation s with what we have now derived it to be when we want to do the forward. We're going to do now the forward rule replacement, or replace s with the appropriate z expression to obtain the forward rule discrete equivalent. And the forward rule, again, was simply replace s with this factor z minus 1 over t. If we do that in what we just derived, we can now say that we have z minus 1 over t, that's the s, times capital X of s, equaling A X of s plus B E of s. Let's multiply through by capital T to clear that fraction, and we now have z minus 1 capital X of s equal to AT X of s, and here don't get confused. Capital T is just a scalar number. It's not a matrix, but it is a capital variable. BT, so that's just the original continuous time input matrix B scaled by whatever the sample period is, capital T, E of s. We can now put all of the appropriate powers of z and combine the variables with each other, or what I'm really trying to say is let's just keep the z x of s on the left. Actually, I'm sorry. We've now moved into the z domain, so let's now go ahead and replace all of these arguments of s with z. So we've gone from s domain to z domain, so I should have been using as the argument on these variables that have been Laplace transformed the variable z. Sorry about that. So now we've gotten rid of all the s's, we've replaced them with z. Remember, the only s that we needed to substitute this z minus 1 over t was the operation of s and not the argument of s inside the bracketed expressions. So now we have a expression for x of z in terms of e of z. We now have z capital x of z is equal to, I'm now going to move this term over to the right hand side, so I'll add capital X of z to both sides, plus at x of z plus bt e of z. That 1 times x of s is equivalent to the identity matrix capital I times x of s. X of s, remember, can be a vector, so that now we have I plus a t capital X of z plus bt e of z. We now can go back into the time domain. This particular expression in the frequency domain, or multiplication by z in the frequency domain, corresponds to an advance of 1 in the time domain. Here, there's no z that's scaling capital X of z or capital E of z on the right-hand side. Those will now just come straight through with little x of n and little e of n, so that the matrix, the system matrix that is now scaling the state vector in the discrete equivalent is now the I plus AT. And the input matrix that weights the input E of n is capital BT. If you go back to our expression that we were trying to find, we were now trying to find matrices that connected E to U, and now we have a dynamic expression available to us in the discrete equivalent. If we simply realize or recognize that this particular matrix is the system matrix phi that we wanted in our discrete equivalent. And this matrix is actually the gamma. If you look at the output equation, and if we take that into the frequency domain in the z space, that's just u of z is equal to c x of z plus d e of z. No s to z substitutions. There's no operator s in that output equation. It's a straight algebraic relationship between the input e, the state variable x, and the output u. That now goes directly to the output setting, and so the c and the d don't change, but we can now say, oh, if we needed to say what is the output matrix in our discrete equivalent, the H is simply C, the C matrix, and the J is the D matrix. With those associations, we now have phi is just I plus AT. So if you now need to go into the discrete time setting to find a discrete equivalent, we can then quickly see that phi is I plus AT. Gamma is BT, H is C, and J is D. And that then represents the discrete equivalent for a numerical integration strategy using the forward technique. Or if you are given an A, a B, a C, and a D matrix in the analog setting, you don't have to do any matrix exponentials. You just scale the system matrix in the analog setting A by the sample period capital T and add the identity matrix to that, and that now becomes your system matrix capital Phi in your discrete equivalent. The input matrix, you simply scale the analog input matrix B by the sample period T. The output matrix C is a immediate equivalence to the output matrix H. Likewise for D if you do have a direct feed-through matrix. And that means that using the forward strategy, it's pretty easy or quick to find a discrete equivalent state space representation using the forward numerical integration strategy.